Okay, last part of chapter 10 is tangent lines and how those interact with chords, radius, diameter, all the angles we've talked about. As a reminder, from the beginning of the chapter, a tangent line is a line running along the edge of a circle that only touches at that red point. Okay, so the red circle that is called a point of tangency, which you will never hear again in C, but it's in the curriculum, so now you've seen it. Okay, first example. Now you're going to be given a little bit more things to figure out, particularly with angles. So, you're given angle at B is 50 degrees, so where it's not F. This is the angle at 50. Okay, and then you need to find all of these. So, B, D, C, D, C, E, triangle C, D, E, as in what kind of triangle is it, and then the angle at D, E, C. So, to begin with, looking at B, D, C. So again, when we're talking about angles, the letter in the middle is where the angle is at. So B, D, C, that's really messy, but you see the point. Right here. So we're looking at the angle right there in the corner. As we said before, at the beginning of the chapter, a tangent line, which is what A to B is, intersected at the radius. So the radius is, of course, C to D. That angle there will be, let's erase this again, always 90 degrees. I know it doesn't exactly look like it in the drawing, but it will always be 90 degrees. So for the first part, angle BDC is 90. Second one now. Now we're looking at DCE. So we know that D is 90, B is 50, so the last thing you have to do first is find the angle on the other side, right here. So to do that, just take 180, subtract 50, subtract 90, you get that blue angle to be 40 degrees. So the last part is to then find this angle at the green line. So we know a straight line is 180 degrees. We've done that before. So F to E is 180 degrees. Now that first part with the blue, I don't know where the rest of it went here, is 40. So to find the angle at C, so we'll switch that to green. So angle DCE, 180 degrees for a straight line, minus 40, you get 140 degrees total in the end. Okay, so now just to finish things off, triangle CDE is an isosceles triangle, meaning the length from C to D is the same as C to E. They're both a radius, so that makes sense. And it also means that the angle at D is excuse me, is the same as the angle at E. So now to find angle DEC, we know the angle right here, that green line, is 140 degrees. So to find angle DEC, 180 degrees for a triangle, subtract the angle you're given and divide by 2. So 180 minus 140 is 40 degrees. divided by 2 is 20. Now the next two slides explain everything you just saw just in words, so you can always go back to it in that regard. So this will be the first two we did, angle BDC and angle DCE. And then here is how you figure out that triangle CDE is an isosceles triangle, and finally the last part, the angle at DEC. The next example, now we're looking at chords. So using what you know about tangent lines and chords, you have to answer another series of questions. So it wants you to find the length of this diameter from B to D. Looking at the triangle you're given, you have the length of the hypotenuse, which is 25. The length of the base is 7. There's 25 and 7. So we're just going to use Pythagoras once again, everyone's favorite. So we're looking for a diameter. So A. Okay, so using Pythagoras, A squared plus the base of that triangle is 7 millimeters. The hypotenuse for C is 25 millimeters. So solving that, like you all know how to, if we've done it repeatedly, you get A to B 24 millimeters. Okay, now using this information, you can find the length from B to E. So triangle BCE is an equilateral triangle, so each length is the same. Looking at B to C, that's a radius. C to E is a radius, which means that B to E will be the same length. So with a diameter of 24 millimeters, the radius will be 12. So the length of B to E is 12 millimeters. Okay, two more for this one. Now you need to find the angle at B to E to D. This angle is an inscribed angle like we did in the first part. It is opposite the diameter. So if you remember, we talked back then, any angle opposite the diameter will be 90 degrees. So for C, measure the angle is 90. Last part is to find the length of the line from D to E. So this line right here. Okay, we know that B to E is 12 millimeters from the question before, and we know that D to B is the diameter, and that's 24. So again, we're looking at Pythagoras. Okay, so looking for A, base was 12 millimeters. The hypotenuse is 24 millimeters. Square them, subtract 144, find the square root. A will be 20.8 millimeters. Done. The last part. The last thing is, of course, problem solving, because you can't get away with that, not seeing that in Math 9. So you have a race car driver racing around a track. There's a radius of 80 meters and is traveling at 190 kilometers per hour. When the driver loses control and skids off the track in a line tangent to the circle. If the car skids for 108 meters, how far is she from the center of the track to the nearest tenth? So, you draw out the information you're given. You have a radius, which is 80. At this point, she skids off at some line tangent to the track. And then you're looking for how far she ends up off the center of the track. So here's a better diagram of straight lines. So using this information and Pythagoras, you're able to solve this question. So I'll just set it up for you and show you the answer, but I would hope by now that you know how to do all of this stuff. So in this case, we are looking for C because your right angle is there. So you're looking for C. A will solve 80. B will be 108. Equals C squared. Square each one, add them together, find the square root. C will be 134.4 meters. So that's this length right here. 134.4. The rest of the handout is again your diagrams are given throughout. So just work through these questions on page 400 and 401. If you have questions, please track me down or email me, and good luck.